One last example where we can use a Taylor polynomial to approximate some sort of transcendental value. So we have the cosine of negative 0.5, and we want to approximate that using a third degree Taylor polynomial, and then we're going to compute the absolute error. All right, so let's start by defining our function f of x to be equal to cos of x. Let's make it something easy. And we're going to have x, we're going to center it about a equals 0. Okay, so if a is 0, that means we're going to use x to be equal to negative 0.5 when we go through and try to solve this. All right, so to approximate the value of cosine of negative 0.5. All right, so let's make our chart. So we have n, and we need a third degree polynomial. So we're going to have 0, 1, 2, and 3. We're going to have cos of x as our function. So we're going to find the nth derivative of x. Remember, the 0th derivative is always what we started with. First derivative, negative sine x. Then we have negative cos of x. And then we have positive sine of x. And now we're going to substitute back in 0. All right, so this is going to be fn at a. All right, so when we say, we're going to say cos of 0, which is 1, sine of 0, which is 0, negative cos of 0, which is negative 1, and then sine of 0, which is 0. All right, we're going to hold on to these because these are going to be the values that we substitute back in for the third degree polynomial. Now, P3 of x, remember our formula. It's going to be f at a plus f prime at a, x minus a, plus f double prime at a divided by 2 factorial x minus a square. And then finally, plus f3, the third derivative of a, or at a, divided by 3 factorial x minus a cubed. All right. Now, the good news is for us, notice that sine of 0 is 0 for the first degree, or the first derivative, and the third derivative. All right, so in essence, this is going to be 0, and this is going to be 0, which means that these are going to cancel out. Okay, if you don't trust me, you can just substitute them in right away. All right, so P3 of x, in this case, is just going to be, now remember, f at a was 1. All right, so we have 1, and then we have a negative 1 over 2 factorial, so minus 1 over 2 factorial, x minus a, remember a was 0 squared. And so if I simplify what P3 is going to be, not really all that interesting, but 1 minus 1/2 x squared. Okay, so this is our third degree polynomial. Okay, and we're going to use this to approximate cosine of negative 0.5. Okay, so P3 at negative 0.5 is going to be equal to 1 minus 1/2 of negative 0.5 squared. If we really wanted to, we could do this in our heads. It's probably going to work out to be something like a little bit less than 1, but I'm just going to plug it into the calculator here. So we have 1 minus 1/2 of 0.5 squared. It's technically negative 0.5, so it's 0.875. Okay, so this is going to be 0.875. All right, now this is the answer to part A of our problem. And part A asks us to approximate the given quantity using a Taylor polynomial with n equals 3. Right, now let's see if we're anywhere close to this. Okay, because we have to find the absolute value, or the absolute error, excuse me, which does include an absolute value. But let's start by finding the cosine of negative 0.5. Okay, we're going to use our graphing calculators to do that. Make sure that you're in radian mode, okay, when you're doing this. Okay, so if I'm in radian mode, I'm going to find the cosine of negative 0.5, and that gives me 0.8775, and that's pretty close, right? Especially considering that we just had a second degree polynomial. Even though we have P3, the third degree is 0, and it doesn't really contribute anything. Okay, so this is our 0.87758. And we're accurate out to the hundredths place, which isn't too bad. So for our absolute error, that's going to be P3 at the value minus the cosine of negative 0.5. And we're going to take the absolute value of that. So we're going to go back to our calculator. All right. And in our calculator, we're just going to take the absolute value of 0.875 minus the cosine. Okay. And that's what we get out of this. We get 0.00258. Okay. So this is 0.00258. All right. And let me just make sure I copied that down correctly. So 0.00258. Yep. And if I wanted to convert that into scientific notation, that would be 2.58 times 10 to the minus 3. All right. And that's not as accurate as the last one that we got, but it's still pretty decent. Okay. Especially considering that we could compute that by hand if we really wanted to. Okay. To be able to approximate the cosine of 0.5, which we couldn't do by hand. Okay. So the whole purpose of having these Taylor and Power series is to be able to use them to model functions. And as the order of the polynomial increases, the more useful that polynomial is going to be for the most part. So in the next video series, we're going to start taking a look at the idea of how well does a series converge, or what is the radius of convergence, and then also what is the interval of convergence.